A Boeing 737 fights for control as it touches down on a Maui runway, trailing debris and missing 35 square meters of its upper fuselage. This is the Kahului Airport, where Aloha Airlines Flight 243 ended its short trip from Hilo. 35 minutes prior, this was a routine island hop, with most of the passengers on board dressed in summer clothes for a beach vacation. During boarding, one passenger noticed a tiny hairline crack near the main cabin door. She assumed the airline's inspection teams had already cleared it and took her seat without mentioning it to the crew. That single fracture sat at the center of a chain reaction that would force a total recalculation of commercial flight safety. At 24,000 feet, the environment is incompatible with human life. The air is too thin to breathe, and the temperature outside the cockpit windows drops to -45 degrees Celsius. This diagram illustrates cabin pressurization. To keep everyone alive, the plane pumps air inside, creating an internal environment much denser than the outside atmosphere. This effectively turns the aircraft into a metal balloon, constantly pushing outward against the hull. The Aloha incident forced investigators to ask how a rigorously maintained pressure vessel, designed to withstand these immense forces, could simply unzip in midair. As the plane reached its cruising altitude, the internal pressure peaked, and the roof suddenly exploded. The blast obliterated the emergency oxygen systems and instantly swept a flight attendant out of the aircraft. The pilots had to act immediately. With the oxygen masks destroyed, they had only a few minutes to dive towards 10,000 feet before 94 passengers succumbed to hypoxia and lost consciousness. During the dive, the passengers faced 500-kilometer-per-hour freezing winds screaming through the open cabin. The crew navigated between islands to avoid the 10,000-foot Haleakala summit, while struggling to stabilize an airframe that was visibly sagging under the stress. On the final approach, the nose gear indicator failed to show a lock. An emergency belly landing would have likely snapped the weakened fuselage in two and ignited the fuel tanks, leaving the pilots with no choice but to attempt a standard touchdown. The landing was successful, and 94 people survived the ordeal. Forensic teams from the National Transportation Safety Board, represented by this SEAL, arrived shortly after to dissect the wreckage. Investigators focused their attention on the 737's skin, a series of aluminum sheets only 1 millimeter thick. Boeing built these planes using lap joints. This diagram shows how the aluminum sheets overlap, held together by a combination of high-strength epoxy glue and 3 rows of metal rivets. Every time the plane pressurizes for flight, these joints expand. When it lands, they contract. This repetitive motion is known as a flight cycle. Because of its short, frequent Hawaiian routes, this specific plane had endured nearly 90,000 of these cycles, far exceeding the standard wear expected for its age. Years of exposure to humid island air caused the internal epoxy glue to degrade. Without the adhesive bond to distribute the load, the explosive force of the cabin pressure shifted entirely onto the individual metal rivets. This stress created thousands of microscopic cracks around the rivet holes. These fractures eventually linked together, bypassing the safety tear straps and allowing a massive section of the roof to peel away instantly. Boeing had previously warned about this adhesive failure, but Aloha Airlines management skipped the specialized eddy current scans required to find these invisible cracks. The aircraft was ultimately defeated by the accumulation of tens of thousands of microscopic fractures that were never caught during maintenance. The NTSB realized the problem wasn't isolated. When they mandated re-inspections for older Boeing fleets worldwide, they found identical microcracks hiding in dozens of other aircraft. This data changed how engineers calculate an aircraft's lifespan, shifting the priority from total flight hours to the actual number of physical pressurization cycles. The Federal Aviation Administration responded with the 1991 Aging Aircraft Safety Program, forcing stricter inspection protocols across the entire industry. These new rules effectively ended the era of the eyeball test, proving that human sight alone cannot accurately judge the structural health of a high-cycle aircraft. Modern safety relies on eddy current and ultrasonic testing to see through the metal. These scanners detect internal flaws long before they can reach the surface or compromise the hull. Explosive decompressions caused by metal fatigue have been nearly eliminated because of the technical standards established after this incident. Flight 243 proved that aviation safety depends on mastering microscopic threats, ensuring that no modern passenger has to experience